All right, so you should be able to see my screen now. We're going to look over these 4 examples here. On the first example, this is just the basic RC switch, right? It starts off uncharged, you close the switch, it charges up, and that's all that happens. There's no discharging in this example. They don't get more simple than this, which is why I put this as example number 1. So we've got the voltage across the resistor is going to be IR. The voltage across the capacitor is Q over C, and that would be the charge on the capacitor at time C. If we think about the initial conditions of this, at time equals 0, it tells us up here, at time equals 0, the capacitor is uncharged, so we know it's going to have 0 charge on it. And if the capacitor has 0 charge on it, it's going to have 0 voltage drop across it, right? We just said that up here, Q over C. So if Q is 0, voltage on the capacitor becomes 0. So it starts off uncharged. That means all of the voltage is across the resistor. And the initial current in this circuit is going to be the current through the resistor, and V equals IR. So if we rearrange V equals IR, we get I equals delta V of the resistor over R, V over R. And in this case, all of the voltage is over the resistor at the beginning, and they give us a graph of current. And so we can see what the current is at time 0, right? It's the y-intercept of that graph. Be aware that this is in milliamps, right? So don't let that throw you off. Times 10 to the negative third. The final conditions of this thing. This is some long time later. We're going to be at like an infinite time. Okay? You could just say a very long time, but approximately infinity. The final charge on the capacitor, all of the voltage from the battery is going to be across the capacitor at the end. And so Q was, we rearranged this equation here for Q, we get voltage times capacitance. So this is going to be epsilon C. Oops. Let's write that one up. Epsilon C. The voltage across the capacitor is the voltage of the battery. And there is going to be 0 voltage across the resistor because there is going to be 0 current flowing through. The capacitor here, after a long time, will act like an open switch. There's a physical gap here. And so when we think about current flowing, it's building up charge on this side of the capacitor, it's building up charge on that side, but it's not actually flowing through the middle. And so if the battery can't push any more charges onto either side of the capacitor, then you're not going to have any current jumping across that gap. So initial conditions, final conditions, I think that's everything I need to say. Make sure you include units for parts A, B, and C. And then in part D, is the graph going to be linear or curved? You can look back in the previous notes to think about that. And make sure you label intercepts and asymptotes as appropriate. In this case, because we're dealing with numerical quantities, you should have like numerical values on your intercepts and asymptotes there. In other problems, they would just be like symbolic values for your intercepts and asymptotes. In example number 2, this is a slightly more complicated RC circuit. we've got 2 loops here. And initially, it says the switch is in the open position. C is initially uncharged. So we know the initial charge on the capacitor is going to be 0. What kind of relationships do we have in this one? Well, when the switch is closed, this side of the capacitor is connected directly to that resistor. This side of the capacitor is connected directly to that side of the resistor. So the voltage drop across this capacitor has to be the same as the voltage drop across that side of the resistor. Okay? So delta VR1 is going to equal delta V for the capacitor. Okay? If we think about Kirchhoff's laws here, then if we go around either loop, right, the sum of the voltages is going to equal 20. So we can say that 20 is going to equal delta V R1 plus delta V R2. We could also say 20 equals delta V delta V C plus delta V R2. And that's just substituting the first result into that equation. So for our initial conditions, if the capacitor starts with 0 charge on it, it's going to have 0 voltage across it. And if the capacitor has no voltage across it, remember capacitor and R1 are at the same voltage, so that's going to have 0 volts across it. And if R1 has 0 volts across it, if we come back up to this equation here, if R1, this is 0, that means all of the voltage is going to be across R2. So this one will start off with 20 volts across it. And the current here is initially all the current's going to be through R2, right? And then at first, all the current is going to tend to go this way because this has like 0 charge on it. So the charge is going to build up. But as soon as, even a little bit of charge goes here, you're going to have some current going down this way as well through R1. But all the current will go through R2. For the final conditions here, they just say a long time after the switch is closed. Okay. So this is just a long time. You could put infinity there either way. Well, we can find some of this information from the graph that they give us, right? We can see the asymptote here is 12 volts. And that 12 volts is going to be the voltage across the capacitor, but it's also going to be the voltage across resistor 1. So at the end, we know this is going to be 12, and that's going to be 12. The voltage drop, did we get that right, R1? Yeah. The voltage drop across R2 is going to be 8, right? Because delta V R1 and delta V R2 have to add up to 20. So 12 and 8 are going to equal 20. The charge on the capacitor, you can find that from using C equals Q over V and just solving that out. And for the final current, basically all of the current's going to go through R1 and R2. None of the current's going to be going through the capacitor. So all the current's going to be going through R1 and R2. And R1 and R2 are basically in series, connected to the battery. This is a long time after it's been charged. All the current goes through R1 and R2, and they're basically in series. And then you have this capacitor hanging out in parallel, which is already charged with the same voltage drop as R1, and it basically has no effect on the circuit after it's gotten charged up. So one way that we could model the equation a long time afterwards would be like this. Right. R1, R2, and that's it. I mean, the capacitor over here has no current flowing through it. And so really this is just like a little simple 2 resistor in series circuit. For the purposes of finding the current, that's a good way of modeling it. It looks like the screen may have frozen up on me here. Let me try stopping the screen share and then starting it again. All right, let's go back to the screen share. I think there was just a lapse error there. Okay. So I don't know exactly where it's frozen up. But for the final conditions, after a long time, the voltage across the capacitor was at 12. We got that from the graph here, voltage on the capacitor, 12 volts. If that was going to be 12, then this is going to be 8, and this one had the same voltage as the capacitor, 12. It's saying my internet connection's unstable, so this might drop out. We'll see. Hopefully it stays on. And then this was the little model that you could use for the long time later. All the current flows through R1 and R2. They're basically in series, and there's no current flowing through the capacitor. It is hanging out there, but it's not really affecting things. All right, number 3, another more complicated circuit. When the switch first gets closed, we have 2 loops in our circuit, right? We have this loop here, which I'll call loop number 1, and then we've got like this loop here, which I'll call loop number 2. For loop number 1, we know that V0 minus delta V for the capacitor minus delta V R1 equals 0. For loop number 2, we know that V0 minus delta V R2 equals 0. Basically, that just says that delta V R2 equals V0. And we can see that because R2 here is connected directly back to the battery. So the current through R2 is going to be steady the entire time that the switch is closed. The current through the capacitor and resistor here is going to initially, since there's no charge on the capacitor initially, this is going to be 0, and the current through here will be V over R1. And then as charge on the capacitor builds up, you'll have a voltage drop across the capacitor. That means the voltage drop across this resistor R1 decreases. And as the voltage drop decreases, the current is going to go down as well, right? Because V equals IR. So if V goes down, I must go down as well because R's constant. So for our initial conditions here, delta V for R2 was V naught. Delta V on the capacitor is 0 because the capacitor is uncharged. The current through loop number 1 is going to be V over R1. And through loop 2, V naught over R2. And delta R1 had the same voltage drop as the voltage supply. So when the switch first closes, it's like the capacitor is not even there. It acts like a short circuit. And that's true anytime you have an uncharged capacitor and then you apply some, like you close the switch and it's connected to a battery, it's going to act like a short circuit. And then as the voltage drop across it grows, the current is going to slow down until it stops once the battery can't pump any more charge onto the capacitor. In part C, they ask us how much energy is stored in the capacitor a long time after the switch is closed. So let's think about the conditions a long time after the switch is closed. A long time after the switch is closed, all of the voltage drop is going to be across the capacitor, and no current is going to be running through R1. We will still have current flowing through R2, but no current will be coming down that middle branch. So the voltage on the capacitor is now going to be V0. The voltage across resistor 1 is going to be 0. The voltage across resistor 2 is still V0 because it's connected directly to the battery. Whatever happens with the capacitor doesn't change anything about what happens to R2 anytime during this deal. So the current through resistor 2 is still the same, V naught over R2. The current through resistor 1 is going to be 0. The time here, it just said, a long time later. And the charge on the capacitor, you can figure that out based on the voltage and the capacitance. In part D now, they say that the switch is opened. And what happens when we open the switch? Now the capacitor is charged. When the capacitor is charged and we open the switch, it's like the battery side of the circuit, like all this stuff, it's like it's not even there. It does nothing. So if I was going to model this as a visual way to look and understand what's happening, this is what we have. We have capacitor connected to R1 and R2, which are going to be in series with each other. The initial charge on the capacitor here is QF from part C, right? So this final capacitance right there is what you put down here. The initial current is the same through I1 and I2. So I1 equals I2 equals, we could just call it I. It's all the same. The equivalent resistance is going to be R1 plus R2 because these are now in series. And we know that delta V for the capacitor is going to equal I R EQ. And delta V for the capacitor was delta VC from part C again, right? The charge that it starts with is the same as the charge that it ended with in part C, which was the same charge as the battery, right? Okay, so I think that gets you enough for number 3. Let's go on and look at number 4, and then we can take some questions. Number 4 is the most complicated one, and why I saved it for last. If we have the switch open, it's like the switch is not even there. Those little bits of wire that dangle down here and there make no difference. So I drew the circuit again. That might help you see what we have a little more clearly here. What we have really is 2 basic RC circuits in parallel. Okay? But each of these will follow the basic rules of an RC circuit. So each one of those is going to follow the same set of basic rules that we already covered in the first part of the notes. Okay? So you can go back and you can look at what's happening here. Initially, the current through this bottom branch is going to be epsilon over R1. And this current through the top branch is going to be epsilon over R2. And if you wanted to find the total current, you would add epsilon over R1 plus epsilon over R2. And that would be the initial current, like the second that the battery was connected. I don't know that they're asking about that. After a long time, what happens? Well, we know in an RC circuit that after a long time, the capacitor reaches the same voltage as the battery. And that's going to happen for both of these capacitors. And after a long time, a capacitor in this kind of situation doesn't allow current to flow through it. It acts like an open switch. So after a long time, and these have reached like a steady state, they've both charged up, no current through the bottom branch, no current through the top branch. So there is no current flowing a long time after these have been charged. They are completely charged, and there's not a physical path for charge to flow from one side of the battery to the other side of the battery. It can't go across the capacitor because they are literally, a gap of empty space. Unless you had a super strong battery on there, or a very, very small gap, you'd have to spark the gap, right? You'd have to figure out what the breakdown electric field for that material was, and then figure out if your voltage difference across the capacitor is enough to create the breakdown electric field. So that's some of the just behavior when it's open. When it's closed, this is how I model the circuit. Okay? This is exactly the same as what we have up there. It's just drawn in another way. But I think it might help you to understand some of the relationships that exist here in a more concrete visual fashion. The voltage drop across R2 is going to equal the voltage drop across C1. Right? That has to be the case because, look, they're directly connected by a wire here. Anything that's going to be connected by a piece of metal is at the same voltage. So this side of the resistor is at the same voltage as this side of the capacitor, and same with the other side. And that is also true of our second pair over on the right. Delta V R1 equals delta V C2. Saying my connection's unstable. Hopefully this will hold on. We're almost done. We have our battery there, epsilon. We can also say that if we do a big Kirchhoff's loop here. So for my Kirchhoff's loop, I'm going to go this way and then that way and come back around. If I did that loop, epsilon minus delta V R2 minus delta V R1 equals 0. And once the current is allowed to come back to a steady state in this configuration, steady state means that the capacitors have readjusted themselves and the current's not changing anymore, right? It's steady. Once that happens, this pink line that I drew will be the path of current. There's not going to be any current flowing across a capacitor, right? When it's in steady state, the capacitor is going to be charged. And when the capacitor is fully charged, no more charge is entering or leaving. So there's no current that goes across the capacitor set. The current will go through those resistors. And how would you model that path that I just drew in there? What is that really? Well, it's a resistor in series with a second resistor, right? And so we know that the equivalent resistance is going to be R2 plus R1. And we know that V equals I R EQ. Okay, a little bit of a delay, but I think it popped up for you. So let's see if we covered everything that we need to for that problem. Steady state current through the ammeter when it's initially open. Yeah, it's just the current from the first branch plus the current for the second branch. The charge on the 10, the steady state current is different than the initial current, right? Be aware here, this steady state current is going to be after C1 and C2 are charged. While they are charging, the current is not steady state. So the initial current would be, epsilon over R1 plus epsilon over R2. But that's not the steady state current. The steady state current, I talked about that earlier, that was going to be 0 because these act like open switches. The charge on these, you can use the basic rules we went over before. The energy, we wrote down equations for that on the front page, and we've done the energy and capacitor equation previously. The new steady state current through the battery, I talked about that down here. And the final charge on the 5 microfarad capacitor, that was this one. The charge on here you can find if you know the voltage across here, and you know the voltage across here because it's the same as the voltage across resistor 2. And if you know the current through resistor 2, you'll know the voltage across resistor 2. So I think that gives you everything you need to do these 4 problems. And hopefully everything that I said made sense. And it shows you a little bit more about how to break these situations down, to draw initial diagrams, final diagrams, to think about how the capacitors act in those situations. And so you'll finish these ones up on your own, and I'll post the keys sometime later. Let me stop sharing the screen now.